All right, so remember the EVT without looking, right? The EVT says if a function is continuous on a closed interval, then not only will it take on all the y values between the y values of the endpoints, that's the IVT, but also it'll what? It'll have both a max and min. Good. And if we just say max and min and don't qualify what type, everyone knows we're talking about which type? Global, also known as absolutely. Good, absolute. So let's go ahead and figure out how to use the EVT. Okay, this is called the closed interval method for finding extrema, and it's pretty easy. So if you have a function that's continuous on a closed interval from A to B, then the EVT guarantees a max and min, and it can occur at one of two places. It can occur at a critical value on the interior, or it can occur at an endpoint. Right? That's it. And remember, very often the endpoints themselves are critical values. So the easiest way to play this game called Extrema is to take the derivative, find your critical values, and then once you have your contestants, which are endpoints and critical values on the interior, the game itself is played simply by finding the y value at those points. And at the end, the biggest y value is declared the maximum, the smallest y value is declared the minimum, and then anything that's in between didn't win the game and goes home with a free toaster. Okay? Thanks for playing. All right, so if this were a game show, the redhead on the left would be the left endpoint, the creepy dude on the right would be the right endpoint, and the fist pumping girl in the middle would be the interior critical value. So if their scores were the y values, there's two winners. Who would be the absolute maximum winner? Creepy guy. Creepy guy is the maximum winner, right? And he ended up being the right endpoint. And then who would be the other winner? The absolute min? The midpoint, right? The fist bump girl. And then the redhead, she goes home with the free toaster, right? Which is not, it's not a bad gift. It's not as bad as it seems, okay? But it's nowhere near as special as bragging rights, right? So let's play the game. Example 7, determine if the EVT applies, and if it does, find the extrema on that closed interval. All right, so we have a closed interval. That's good. That's one of the requirements. So the endpoints are in the house. Team endpoint actually is already here, right? -1 and 2, they're contestants. We'll put them in the green room for now because we need to see if the EVT applies, if we can even play the game. And if so, we need to find the critical values on the interior. Well, what type of function is f of x? Polynomial, good. And where are polynomials continuous and differentiable? Everywhere. So does the EVT apply? Yes. And you don't have to be super specific. Just say EVT applies. EVT applies, comma, because f of x is continuous on, and then you specify the interval from -1 to 2. You don't want to say it's continuous for all real numbers. You always want to speak specifically to the theorem itself, which is that closed interval. So the IVT, for what it's worth, also applies, but that's not what we're after in this case. So we need to find the critical values, right? So let's find the derivative. F prime of x is going to be 12x cubed minus 36x squared. Now remember, I told y'all to always consider the ones where the derivative is undefined first. The derivative of a polynomial is another polynomial. So is that derivative ever undefined? No. So at least we've considered it and not just like forgotten to consider it. So we're only interested in the ones where it's equal to 0. So we don't have to go down the fork and do it two separate times. We could just set that equation equal to 0. And of course, once it's equal to 0, we F it. Right. Very good. Is that what you were saying? Or were you going to say freaking F it? Oh, factor it. Okay, that's what the F word is in here. Good. So we factor out a common factor first. That's 12x squared. And that gives us x minus 3. And of course, then we can rattle off the critical values, right? X equals 0 and x equals 3. Now, for sure, without a doubt, those are critical values of the function, right? But in order to play the game, since we're on the interval from -1 to 2, we need to make sure that they live on the interval, okay? And there's no guarantee that we're going to have a critical value on the interval. We just have to compare. Are either one of those on the interval from -1 to 2? Yes, right? 0 is. So 0, congratulations, you get to play the game. And 3, yeah, maybe try again to be a contestant on a different show, okay? So that's super important, okay? So now we have critical value. So let's play the game. The way I play the game is I list them vertically here. I got f of -1, and then f of 0, and then f of 2. So if you want to list them side by side like that, or vertically, you can then work out in rows, or you can list them along the top. But you do want to do them in increasing order, okay? So let's go ahead and evaluate now. And this feels like algebra 2 here, really. We're plugging in a -1 to f. So help me out here, because this is not fun, right? It's boring. So we get 3 plus 12, that's 15, right? Plug in a 0 and you get 0. Plug in a 2 and you get, holy moly smokers, 2 to the 4th, that's 16 times 3, 48. I'm going to write it down. There's no reason why we can't write down intermediate steps. Minus 2 cubed is 8 times 12 is 96. So that ends up being -48. Oof. Okay. And that's enough. So this right here, the computation of your y values at the endpoints and at your critical value, that is the justification. And now we just answer the question. So f has a maximum of y equals what? 15, good. At x equals -1, and a minimum of -48, good, at x equals 2. So in this case, team endpoint swept the competition. But that's all right, okay? If you were to graph that on that closed interval, the left endpoint would be the highest point on that of the graph on the interval, and then the right endpoint would be the lowest. So that's it. That's how you play the game. It's that easy, okay? Now, while we're at it, let's review our first derivative test. Remember, we just kind of learned that in the warm-up. Since we happen to have both critical values for f prime, let's see if those are local max or local mins or neither. So using the first derivative test, this is kind of getting ahead, but again, we have the information, might as well use it. We're going to have our x and then our f prime row, and then now we're going to consider all the critical values. Here's 0, here's 3. So I pick any random number from those 3 intervals. So to the left of 0, how about -1? Any number between 0 and 3, how about 1? And to the right of 3, 4. Now, we plug it back into a full-fledged factored version of f prime, okay, which is this one here. And again, if we can simplify the calculations, because we're only interested in sign, we could do that. 12 is always positive, x squared is always positive, so the sign of the entire derivative is determined exclusively by the sign of x minus 3. Yeah, so when you plug in a -1, you get -1 minus 3 is negative. When you plug in a positive 1, 1 minus 3 is still negative. And when you plug in a 4, 4 minus 3 is positive. Okay, so not only do we now know the intervals where f is decreasing and increasing, this is over its entire domain, let's go ahead and say that. F is decreasing on the interval from -infinity to 0, union 0 to 3. It's actually monotonic decreasing through 0, but you could step over it, and increasing on the interval from 3 to infinity. Make sure when you come back and you answer the questions, you're using the critical values again, because those other x values we chose, those are just throwaway test values, okay? Now, by the first derivative test, notice there is no sign change in the first derivative on either side of 0. So that's going to be decreasing through a horizontal tangent. So that's going to look something like that. But at 3, f prime is negative to the left and positive to the right. So f changes from decreasing to increasing. So that's going to be the location of another local what? Min, right? So we'll just say f has a local min at x equals 3. If you needed to know the minimum value itself, it would be f of 3. And then if they ask you to justify, you have to talk about the first derivative sign change. It's called the first derivative test, so you have to talk about the first derivative. Since f prime changes from negative to positive, not in France, but also at x equals 3. So you say it twice. That's the location of the local min, because that also happens to be the same place where f prime changes in this manner. So you don't even have to say anything about f going from decreasing to increasing. That's understood when you say f prime changes from negative to positive. Okay, now sometimes it'll ask you to determine at every critical value if there's a local max, local min, or neither. So here's what it would look like if you had to address 0. F has neither a local max nor local min at x equals 0, comma, since f prime is negative. We don't want to say on both sides, because when you say on both sides, that kind of implies forever. So the word that gets it with the College Board is negative on either side of x equals 0. That word either is a local argument. It implies immediately to the left and immediately to the right. The sign of f prime is negative. Now notice in the warm-up, when I said there was a local min at x equals 3, I went ahead and restated that f prime of 3 was 0. You wouldn't need to restate that if you already found that over here, right? We already took the derivative and we saw that that 3 made the derivative 0, okay? So you don't have to restate it. You're welcome to, but if you've already found the critical value on your own from setting the derivative equals 0, then that part of the argument's done, okay? So now we're just saying that there's a local min, okay? Cool. So we're doing 2 for 1 here. We're doing EVT, which is a closed interval argument, local absolute max, absolute min, and then we're doing a first derivative test, which is only for local extrema. And we do it over the entire domain, okay? So a 2 for 1. All right, we'll keep that kind of going here so we can kind of speed up the process. Yes, yeah, this would be, we sometimes need to address every critical value, whether it's a local max, local min, or neither. So we haven't really seen the explicit instructions yet, but sometimes it just says, determine the local extrema and then justify, in which case we would just need to say where they are. And then sometimes it'll say at each critical value, determine if f has a local max, local min, or neither. So if you read that, then you have to address the one that isn't a local max or min, okay? All right, so example 8 is also very similar to what we did on the warm-up, but let's do it in the EVT context first. Determine if the EVT applies, and if so, find the extrema. Again, extrema means absolute or global, and it means max or min. So we have a closed interval from -8 to 1. That's good. We just need to see if this function is continuous on that interval. Well, another version of this, of course, is 2x minus the cube root of, or 3 times the cube root, sorry, 3 times the cube root of x squared. And so the domain of this is all real numbers, right? Now, if you remember, and I didn't make this point because we got interrupted by the fire drill, but I did make the point last Thursday at the end of class, bless you. We should be kind of on anticipatory alert for possible vertical tangents, possible cusps. Because we have a fractional exponent between 0 and 1, we know then that when we take the derivative using the power rule and subtract 1, it's going to make that exponent what? Negative, which means that x is going to be thrown into the denominator, which means now we're going to have a value that makes the derivative undefined. Okay, so I said on Thursday, I said that whenever you have a fractional exponent between 0 and 1, you want to be on cusp alert, right? Or vertical tangent alert, really, but cusp alert sounds better. And not only are you on cusp alert, but it's going to be at the root of whatever the base is. So in the warm-up, I think it was x minus 1 to the 2/3. So the root of that base was x equals 1. So we had a vertical tangent at 1. Here, the root of the base is 0. So I know there's going to be a vertical tangent at 0. I don't know if it's going to be a local max or min, but I know there's going to be a critical value at 0. Okay? So anyway, we're on cusp alert. But there might be more. Let's do the EVT first. This function is continuous on the closed interval. So the EVT applies. And simply you just say, because f is continuous, you don't have to prove it, you just have to know that it is, on the closed interval from -8 to 1. So we know that that function on that closed interval is going to be guaranteed to have both an absolute max and an absolute min. And it can occur at either the endpoints, which we have 2 of them, x equals -8 and 1, or at any critical value on the interior. So that's our next task. We have to go out and canvas for contestants. So here we go, f prime of x. The derivative is 2 minus, and then 3 times 2/3. That's another 2x to the -1/3. Now, because we want to use this derivative, I would say don't set it equal to 0 and separate the terms. You can either factor out least powers, or in this case, maybe you wouldn't even think to do that because the first one doesn't even have, a variable in it. So you could do it like that, put it in the denominator, and now get a common denominator. You always want to try and keep your derivative fully intact. Okay, so we need to get a common denominator, which means we need to multiply the first one by x to the 1/3 over x to the 1/3. This is the same as factoring out an x to the -1/3 from both, but we'll just show this option. So that gives you 2x to the 1/3 minus 2 now, all over x to the 1/3. And if you wanted to, you could even factor out the 2 and give yourself the cube root of x minus 1 all over the cube root of x. There is your full-fledged factored version of f prime. Okay? Here's the other option that I wouldn't want you to do. Just set this equal to 0, bring this across, right? This is what they teach in Algebra 2. Divide through by 2, and then cube both sides, and you get x equals 1. Sure, that's going to give you a way to solve the equation, but it's at the expense of the equation. You scrap the equation, it's gone. And you want to preserve it, especially when we're looking for local extrema, because as you already saw when we made the number line chart, we need to come back to that equation. So go ahead and figure out where f prime is 0 or undefined. Ms. Corby. Yes, I certainly will. This meeting. Right. So anyway, because now we are looking for critical values, we already saw that there was going to be a cusp. So we're going to use this twice. So now we're going to say f prime equals d and e, consider it first. That's when the denominator is 0. Well, now if you cube both sides, you get x equals 0. And notice when you do it this algebra way, this is the type of person that's going to even forget to consider, this would be negative, the person who would even forget to consider when the derivative is undefined. So don't do that. So this is going to be your vertical tangent for what it's worth. And now we set it equal to 0, which means we set the numerator equal to 0. Kind of like we did with implicit differentiation. It's kind of the same idea. And now, it's minus 1, sorry. X to the 1/3, we divide by 2, set it equal to 1. Now we cube both sides, we get x equals 1. This is your horizontal tangent. Now, in terms of the EVT, I'm going to create space here, we don't need that. In terms of the EVT, we know there's going to be an absolute max and a min on that interval. Are either one of those values on that closed interval? Both of them are, right? We already had the one. He was representing team endpoint already. He's also a critical value. So this guy's going to play for both teams, kind of like a full-time quarterback, okay? So we don't really need to include it twice. So we're going to figure out now, I'm going to do this one horizontally. So we'll do f of -8. There's the left endpoint. We have a critical value of 0 on the interior, and then we have f of 1. So this is the closed interval argument. This is the EVT. All right, so to evaluate f of -8, we plug it back into the original equation. And that's where this version of the equation could be more useful, right? We tend to think more in terms of radicals when we're evaluating. And again, because we're squaring it and cube rooting it without a calculator, we should go small before we go big, right? Take the cube root before we square it. So plug in a -8 and you get -16. You can write down these intermediate steps. And then the cube root of -8 is -2. -2 quantity squared is +4. 4 times 3 is 12. So -16 minus 12, that's -28. Okay, f of 0, that one's easy, right? That's just 0. And then f of 1, plug in a 1 and you get 2 minus 3, which is -1. So really, now we just go to the judges. Judges, which of those is smallest? Judges, which of those is the biggest? Okay, so f has a min, and again, this is a absolute min, it's a global min of y equals -28 at x equals -8, and a max, a global max, an absolute max of, and this is kind of funny, what's the biggest y value on that interval? 0, right? Some people who are in severe debt would just love to get back to 0, right? Of y equals 0 at x equals 0. So there's your EVT. Oh, by the way, how would we know that somewhere on this interval also the y value is -10? IVT. Let's review that since we're right here, okay? Since f is continuous on the closed interval from -8 to 1, okay? And then if I did mention -10, -10 falls between the y values of the endpoints. So for the IVT, it's about the inequality. So since f is that, and since, then you write the inequality, -28 is less than, I chose -10 arbitrarily, which is less than -1, those are the y values of the endpoints, comma, by the IVT, there is an x value in the open interval from -8 to 1, such that f of x equals -10. Okay, so this is a good time to review the IVT. The IVT and the EVT have the same if part. Okay, so I could have chosen any value between -1 and -28. I just happen to choose -10. That's by the IVT. Okay, now shifting gears here. Does f of x, the function, over its entire domain have any local extrema? Okay, local extrema. Well, local extrema can only occur at critical values on the interior, not at endpoints. So we're looking at the entire domain. So do we have any critical values? Yes, we have 2 of them, okay? And we wouldn't care if they're in any interval because we're looking over the domain. So now what we do to determine if they're local max or mins is we set up our number line chart. So we're going to have x and then f prime, and then here is 0, and here is 1, okay? Now, we're going to be plugging this back into the full-fledged factored version of f prime. This is another reason why we want to get in the habit of not obliterating the derivative, but preserving it, okay? So we're going to be taking the cube root of a number. So let's choose numbers in our number line that might actually be easy to take cube roots of. Something to the left of 0 that's easy to take the cube root of? -1. Something to the right of 1 that's easy to take the cube root of? 8. Perfect. How about something between 0 and 1 that's easy to take the cube root of? How about 1/8? Yeah. I mean, 1/2 would work because we're really only interested in sign. But again, if you choose values, judiciously, it could make it easier. So I don't need to worry about the 2 because the 2 doesn't change the sign. Now, if that were a -2 that I factored out, now it's important because it changes the sign. So what do I get when I plug a -1 in to this derivative? Well, the cube root of -1 is -1. -1 minus -1 is a negative number. So I'm just going to put a negative in the top divided by. That way I don't have to keep track of everything. And then in the bottom, the cube root of -1 is -1. So what's a negative divided by a negative? Positive. This number line chart is only for your own benefit. So if you need to put intermediate signs down, that's up to you. All right, let's plug in a 1/8. The cube root of 1/8 is 1/2. 1/2 minus 1 is positive or negative? Negative, yep. And on the bottom, the cube root of 1/8 is positive. So a negative divided by positive is negative. And then plugging in an 8, finally, the cube root of 8 is 2. 2 minus 1 is positive. And on the bottom, the cube root of 8 is positive. Positive is positive. Okay? Now, the -1, the 1/8, and the 8 have served their purpose. So this is where I've seen students make careless mistakes. We now refer back to the critical values. So let's go ahead and list the increasing, decreasing intervals first. F is increasing on, and it looks like everywhere to the left of 0, so from -infinity up to 0, union to the right of 1, so 1 to infinity. And it's decreasing between 0 and 1. Okay? If there's no discontinuities, then the only place where a function can change increasing to decreasing or vice versa is at a critical value. That's it. So that's the first thing that the number line chart gets us. Now the first derivative test, okay? You don't ever have to say by the first derivative test as long as you justify using first derivative. It's helpful to know which ones were which. Remember, 0 was the vertical tangent. This was your vertical tangent, and then 1 was the horizontal tangent. So if f prime changes from positive to negative at 0, is 0 the location of a what? Local max or local min? It's a local max, right? Because f goes from increasing to decreasing. Now, when you know how it goes from increasing to decreasing, it's even better. It increases to the left, and then it goes vertical, and then it decreases on the right. So this function is going to have a little cusp right there, okay? So let's just justify. F has a local max at x equals 0. Again, if you wanted the y value, it's f of 0, comma, because f prime changes from positive to negative, not in France, but at x equals 0. I've graded AP calculus papers, and I know that that sentence will get you full credit, all right? And then the other one was your horizontal tangent. If f prime goes from negative to positive, that means f goes from decreasing to increasing, so that's the location of a local min. F has a local min at x equals 1, comma, because f prime changes from negative to positive, again, not in France, but at x equals 1. So you list it twice. Here's where it occurs because that's also the same location where such and such happens, okay? Now, this would be a good time to verify visually from a graph, okay? We found a lot of information. So if you want to look on, you can. I'm going to pull the calculator up here. Whoa, big calculator. Yum. There we go. Okay, oops, I have to do it again. That's usually not the case anymore. Usually happens on the first try. There we go. All right, so let me go ahead and get the equation into y1. And it is 2x minus 3x raised to the 2/3 power. Now, the first thing I want to do, let's look at the EVT first, okay? So on the EVT, if I go to my window here, and I only look on the interval from -8 to 1, that's the interval in question. Usually I don't know what to do for the y values, but I found the y values. So for my y min, I'm just going to go to -35, something that includes -28, and my y max, I can leave it at 10. What the heck? Okay, I'm going to hit graph and see what happens. Come on, graph. Come on, graph. I wish the calculator played music in the background. Whoa, okay. So first of all, looking at the graph now, the lowest y value, obviously at the left endpoint, yes? Indubitably. If you hit trace, -8, enter, you get, there it is. Now, it's really hard to see what's going on near the origin here because we have it so stretched out, but we know what's happening there, right? Look over here. What's happening at 0? There's a little local maximum there, right? There's a little local maximum. So now that we know that, let's go ahead and come in a little bit closer. Let's go from -1 to 1, and let's trim some of this off. Let's go from like -5 to 5, and we'll get a better visual. So I still have my right endpoint at 1, but now you can clearly see what's happening. Yes? So when you're comparing those other two to see which one's taller, okay, because the min was at the left endpoint, there's 0, we get 0, and then the right endpoint of 1 was -1. So you can clearly see that it's 0. All right, and then if we hit zoom 6, which is over the entire domain, well, not the entire domain, but you know what I mean. There it is. So what the graph is doing is it's coming in at the origin and it's going vertical like this, and it has a pointy cusp, and then at 1, it's hitting its local min at a nice horizontal tangent, and then it's increasing forevermore after that. So that's pretty much what we established with our intervals of increasing. It's increasing up to 0, and then it's increasing past the local min, and then it's decreasing between the critical values. See? We got all that information just by doing a little bit of calculus, and then the graph afterwards, we're not verifying that we were right. We're actually verifying to see if the calculator knows what it's doing. All right, calculator, well done. You are almost as smart as we. Okay, okay. Fun, fun, fun. So got a lot going on today, right? EVT, practice, IVT, review, and then first derivative test, learn, right? All right, cool beans. Example 9 is trig. You want to do it? Yes? No? No? Yeah. We all know the unit circle. Okay? It's just another EVT example. It is continuous on the closed interval. It's just going to involve evaluating at a bunch of funky angles. So if you want to do that one, you can. All right. So next thing we're going to do here is example 10. If the EVT doesn't apply, does that mean the function doesn't have any absolute max or mins? No. The EVT only gives us the sufficient conditions in which we're guaranteed to have it. Some of y'all look a little forlorn that we skipped the trig. No? No? Abby, do you want to do the trig? No? Okay. All right. So example 10. What do you do if the EVT doesn't apply? Well, I'll show you. It says find the extrema of each of the following over their domain. Well, I'm giving it away. Sketching the graphs. Any information you can collect about the function is going to help you. So again, if it doesn't specify an interval, you assume we're talking over its entire domain. So let's take a look at this function here. What is the domain of this function? This was a good pre-calc question back in the day, right? We can't divide by 0, and we can't take square roots of negative. So if you have just an entire square root contained in the denominator, the radicand normally has to be greater than or equal to 0 to make sure it clears the radicand. But in this case, we don't want it to equal 0 because then we take the square root of 0, which leaves us 0 in the bottom. So 4 minus x squared in this case has to be strictly greater than 0. Now, just to review pre-cal, that is a quadratic inequality. Can we solve it algebraically? No, we can't. Okay, you can either solve it graphically, or you can solve it using a number line chart, like we just did for the first derivative test. I think in this case, it's easier to solve it graphically. This is a parabola that opens down, and it's symmetric to the y-axis. Where are the x-intercepts? Can you tell just by looking at it? What makes 4 minus x squared 0? Plus or minus 2. And we want to know for what values of x is it strictly positive. That means strictly above the x-axis. Well, in that case, it's going to be everything strictly, let me change colors, strictly between -2 and 2. Okay? So there's the domain. The domain is everything strictly between -2 and 2. Diggity darn it, if we were able to include those as brackets, then the EVT would apply, wouldn't it? Because we'd have a closed interval. But without them, shoot. Well, let's see. I know it's not going to be at the end point, but we could still have an absolute maximum somewhere. Let's go ahead and use anything else that we've learned that doesn't require calculus yet. Symmetry, does this function have any symmetry? That's a kind of a cool one. Is it even, odd, or neither? Even, right? If you replace x with -x because there's only one variable and it's squared, it's the same as if you plugged in a positive x, which means it's an even function and has y-axis symmetry. Oh, that's nice. So if I just sketch the graph from 0 to 2, I'll know what it looks like from -2 to 0. Just mirror image it. Okay. Y-intercept, can we get that for free? What's the y-intercept? Plug in a 0 for x and you get 1 over the square root of 4, which is 1/2, right? Okay, so it crosses the y-axis at 1/2. Does it have any x-intercepts? Right, that's when the entire thing equals 0. Well, a fraction is equal to 0 when the numerator is equal to 0. Is 1 over 0? No. Can't have 0 on the top. It's always a 1. Even at Halloween, right? When 1 goes dressed as 0, still a 1 on the inside. Clothes don't make the man. So let's see. I think it's time to BOTC. What do you say? Let's bust out the calculus. Get out the good stuff. Now, I could use the Hody high rule here, but because it's a constant in the top, I think it'll be a little bit easier if I just bring this whole quantity to the numerator and set it was to the -1/2 power. And now I can use the chain rule. Okay? So here we go. F prime of x is -1/2 times blob to the -3/2. We rewrite the blob times the derivative of the blob, which is 0 minus 2x. If we simplify, again, we're after a full-fledged factored version. The -2 and the -1/2 divide out, giving us a positive 1x, which is the only thing in the numerator. And then in the bottom, I could bring the quantity back down, put it under a square root, and cube it. So now I can find critical values. Let's see, where is f prime equal to dne? Well, a single fraction is equal to dne when the denominator is 0. What are the only values that make the denominator 0? 2 and -2. Are those critical values? They make the denominator 0 in the derivative. Are they critical values? Are they in the domain? No. Remember I said at the beginning of class it'd be kind of embarrassing to talk about a function where it doesn't exist? Oh, my egg's on my face, right? Yeah, well, that's why we find the domain first. And that's going to happen. If they're not in the domain of the original function, they're not going to be in the domain of the derivative. So they're going to try and sneak into club critical value because they know that's where it's at. But they don't even exist, right? Get your imaginary booty out of here, right? You're not even in the domain, right? So don't be fooled. Don't let them in. You're the bouncer at the door to club critical value. All right. Now, where is f prime equal to 0? That's when the numerator is 0, and that's 0. So that's the only critical value. I wonder if that's a local max or a local min. You think that'd be helpful to know? Yeah. So let's go ahead and set up our number line chart. X, f prime, 0. Now, we do have to be careful. My domain is -2 to 2. So when I pick a number to the left of 0, I can't go all crazy like -5, right? It has to be something between 0 and -2. How about -1? And then to the right of 0, how about 1? Now again, we plug those into the full-fledged factored version of f prime and look for the sign. What do you know about the sign of the denominator at -1? 4 minus 1 is 3. It's positive, right? So the top is going to be negative. Negative over positive is negative. And when you plug in a positive 1, you get positive over 4 positive, which is positive. So if we were to list the intervals of increasing, decreasing over the domain, we would say f is decreasing not from -infinity to 0, right? But from, or on, we should say, on -2 to 0. And f is increasing on the interval from 0 to 2. That covers the whole domain. You got to be careful. You can't always go to -infinity. Well, I'll be a monkey's uncle. Look at this. F also has a local minimum at x equals 0, comma, because f prime changes from negative to positive, not in France, but also at the same place. So if we're going to be sketching the graph, I know that the y-intercept is 0, 1/2, right? Something like that. And I know that that is a local min, and I know that the domain goes to -2 and out to +2. I know it's decreasing everywhere to the left over its domain and increasing everywhere to the right. Guess what we have at -2 and 2? When you plug it in, you get non-zero over 0. When you plug in a value outside of -2 and 2, you get a negative under the radical. But when you plug in 2 or -2 back into f, you get non-zero over 0. That means there's a vertical asymptote there. There's what the graph looks like, okay? Not only does this function have a local minimum at x equals 0, but it also has an absolute or a global minimum at x equals 0 because of the way it looks, okay? Now, there is a way to change this local argument to a global argument, but we'll talk about that later when you have to justify it. Right now, we're just going to say, okay, f has a minimum of y equals 1/2 at x equals 0 and no max. Okay? No max, no. You cannot go change in the closet. Not today. Okay? So our knowledge of things that weren't calculus limited us, unless we just wanted to like plug in arbitrary values and try to connect the dots. But knowing where there was a local min and where it's increasing, decreasing, combined with the domain, symmetry helped us, but not that much. We were able to sketch the graph and answer the question. Okay? So when the EVT doesn't apply, you could still find absolute max and min. You just gotta use all of your skills, okay, all of them. All right, we got some time. Okay, sweet. All right, any questions on that one? Let's review piecewise functions. F of x. Here's a piecewise function. It is part parabola opening down to the left of 1 and at 1, and it's a line to the right of 1. So is it possible to figure out the domain before we sketch the graph? Sure. The pieces themselves are polynomial, which are defined everywhere. So all we got to do is to see if it's defined at 1. And is it defined at 1? Yeah. We're not saying it's continuous at 1 just yet, but it says use the top piece when x equals 1. So the domain should be all real numbers. Now in this case, you don't want to have to take a piecewise derivative to find critical values. It's a little bit harder. So let's just sketch the graph. The most important x value is 1. So we need to find the limit from the left of 1, the function value at 1, and the limit from the right of 1. So what would be the limit from the left of 1? Plug it in, direct substitution, you get 3, right? Now that's also the function value at 1, so we can put a solid dot there. Solid dot. Yum. What's the limit from the right of 1? Also 3. So for what it's worth, is this function continuous at x equals 1? Yes, because 3 equals 3 equals 3. Okay, good. So now we can finish the graph. To the left of 1, it's a parabola that opens down, and it's reflected down and shifted up 5. So it has a vertex that hasn't shifted horizontally. It's just up here at 5. So there's another point to sketch through. So it comes up like that, and then symmetrically it would come down and then continue. And then x plus 2, well, that's just a line with the slope of what? 1. So it comes out like somewhere like that at a 45. Now it's over its domain. It's pretty much a foregone conclusion, right? We know that there is going to be both a local max and min and an absolute max and min, okay? So let's do, would the EVT, by the way, apply to this function on any closed interval? Yes, the EVT would apply from, let's say, 0 to 2 because the function is continuous at the connecting point. So that makes like a pretty good question. We did that with the IVT, though. So we'll just say f has a max of y equals 5 at x equals 0, and a min of y equals, is this right? 3 at x equals 1. Is that right? Ah, very good. Globally, no. There are no global extrema, right? Yeah, infinity is not a number, though. Yeah, now as soon as I include a closed interval, now we can go back to having absolute extrema, but only on the closed interval. If it's not specified, the interval, then you assume it's over the domain. And there is no global max, no global min. So if I want to say this, I better scoot this over and say local max and a local min. Yeah. It's important that you don't just get casual with the wording, right? Local and relative max or mins can only occur on the interior, and they have to be qualified. Otherwise, everyone's going to assume that you're talking about absolute / global. Okay, and there's another theorem that we have that local extrema can only occur at critical values. So there are only 2 critical values, correct? X equals 0, where the derivative is 0, and x equals 1, where the derivative is what? D and E? Yeah. Okay. So piecewise functions, they're kind of the exceptions to every rule. You kind of look at those either piece by piece, or you sketch them to answer the questions. All right, so that one was a little bit easier maybe than what we needed to do on example 10. Example 10A was a lot of fun. We got to flex our calculus muscles a little bit. Okay, well, let's do one more, and let's use the calculator here again. You'll have questions like this that do involve a calculator, but even though your calculator has the ability to find extrema, there's a max min button. You don't want to use that on the AP exam. Okay, so it says using your calculator's equation solving ability, let's find the extrema of this function on the closed interval. Okay, so rather than just sketch it from -1 to 1 and look at it like we did, let's go ahead and actually play the game one more time, but we'll use the calculator to help us. All right, you ready to play that game? Extrema, everyone's favorite game show. Yeah, all right. Well, we have team endpoint in the green room, -1 and 1. We just need to find critical values. So let's go ahead and find the critical values. We have a function f of x equals x e to the negative x minus 2x. So first, let's take the derivative. All right, this would be good review. We're going to have to use the product rule on that first term. 2 factors means we're going to have 2 terms. So the derivative of x is 1 times e to the negative x just goes along for the ride. Plus x goes along for the ride times the derivative of e to the negative x, which is itself times what? -1. I mentioned when we learned this at first that's for some reason, this is what most people tend to forget. When it's just e to the negative x, a lot of people forget the -1, chain rule. Okay, and then the derivative of -2x is -2. Now the reason we need the calculator for this is because this is not this one doesn't have a closed-end solution. We can't solve this one. Is this one ever undefined though? Will it be? If e to the x has a domain of all real numbers, so this one's never undefined. So we could go ahead and set it equal to 0 right there. Now here's where we're going to use the calculator's equation solving ability rather than its number crunching ability. So we'll come back up here. I'll go to y equals, clear that out. So here we go. Typing it in, second ln, that's e to the negative x. And then we'll say minus, if I clean that up, that's minus x e to the negative x. And then -2. So make sure you double check, triple check that you have it in there correctly. Remember, there is a difference between the subtraction symbol and the negative symbol. The 84s make a distinction. Always graph 0 instead of looking for x-intercepts. You can find intersection points. Now, so we're not tempted by outside x-intercepts. This is where you want to set your window to the window in question. And then -10 to 10 is not bad. That keeps your x-axis in the middle. But I would recommend kind of just stretching it out. Like we saw earlier, sometimes it's too close to the origin. It hangs too close to the x-axis, we can't see it. So stretching it out and keeping your x-axis in the middle would help. So now we'll hit graph. Here comes the derivative. There it goes. There's one x-intercept. You see that? I see it. Hey, if this is the graph of the derivative, and that's the x-intercept over there to the left of y-axis, can we tell just from this graph if that x-intercept is the location of a local max, local min, or neither? The graph is better than the number line chart, right? Because the number line chart only gives us the sign of the derivative, where it's positive or negative. The graph tells us where it's positive or negative and gives us relative values, right? To the left of that x-intercept, the derivative is positive, yes? And to the right of that x-intercept, the derivative is negative. So that location must be the location of a local maximum. Yeah, it is. So let's find it. Second trace number 5. Enter, enter, enter. Come on in. All right. So we get x equals -0.374 or 375. Now, we know that that is going to be the location of the local max. And we wouldn't have to do the number line chart. We could justify it the same way we've been doing. F has a local max at x equals that, since f prime changes from positive to negative at x equals that. But we're after the EVT, okay? So now we can play the game. we want f of -1, f of, I'm going to call this A. This is a nice little strategy. It's 3 decimals. I reported it, but I don't want to use a rounded number. So I'm going to call it A, and I'm going to say that this then down here is f of A, and then f of 1. Now, once I call it A on my paper, here's what I'm going to do. Go to your home screen, and then hit X stow alpha A. And there it is, okay? It stores it temporarily as X. The store button is just above the on button. X, store it as alpha A. Okay, now we're going to be using the function 3 times to evaluate it. So if you want, if you think it's worth it, come down to like Y, I'll just choose Y3. Let's say I wanted to keep F prime in there. I'm going to type in my equation F now into Y3. So X e to the X minus 2X, okay? I don't really care what the graph is. I just want to be able to recall it from Y3. Now I forgot my negative, right? Haste makes waste. There we go. Always double, triple check. X e to the negative X minus 2. Okay, that looks good. So now from the home screen, all I have to do is the following. Alpha trace number 3 of, open parentheses, -1. Write it down, -0.718. Recall it if you want. You don't have to do it in any particular order. So let me do 1 next. -1.632. And then recall it, and then come over here where there's a 1 and put alpha A. And we get 0.204. And I'm not going to finish answering the question, but you could talk about it, right? The EVT applies because this function is continuous on the closed interval. And on this closed interval, f has an absolute maximum of 0.204 at x equals -0.374. Calling it A is okay just as an intermediate answer, not for a final answer. And then which one's the minimum? Well, f has a minimum of -1.632 at x equals 1. Okay, so that's using your calculator to find solutions, x-intercepts, and then using it to evaluate a function. Okay, so that concludes this section. You remember, you don't have to turn in this worksheet. Tomorrow on Tuesday, even though we don't meet, there will be 5 more questions in AP Classroom. The other 5 are due by 4:30 today, if you haven't had a chance to get them done. What's that? There's nothing?
I checked and there's nothing. So I just figured nothing's signed.
There was nothing from last Thursday?
No.
Oh, I saw someone emailed me that it was closed, but I opened it back up this morning and there were 5 questions in there. So you might want to check again. Okay, I can give you another day if you want. I had it closed like on Friday on accident. So if you looked at it after Friday.
No, I looked at it last night.
And yeah, okay, I opened it this morning. Look real quick and see if it's there. Because while you're doing that, I want to show you one other thing.
I don't see it on my end.
Interest. Okay, well then there's no questions from Thursday. There'll be 5 questions tomorrow. Katie, you emailed me and I checked this morning and it was closed, and then I reopened it and I saw them in there. Okay, we'll blame that on College Board. Stranger things have happened. Okay, so no 5 questions from last Thursday. So tomorrow there will be 5 questions that'll be due Thursday by 4:30. The other thing I just wanted to point out is something that you could be looking at in the background. Next time we meet on Wednesday, I'm going to give you a take-home test, and it's going to be very similar to your final. In Canvas, there's a module called Test 3 and Final Exam Practice. I put it on here. It's 20 questions. It's all multiple choice, and the answers are listed at the end. You don't have to do this or turn it in, but it's for you to practice. This one is Form C. Your third test, which will be overnight on Wednesday, that's going to be Form B. And then your final exam is going to be Form A. So if you could do these 20 questions, you should make 100 on your next test and 100 on the final exam. Okay? And so that's in there for you. All right, sweet. I'm sorry about AP Classroom. I don't know.
It won't let me.
It doesn't show anything. Dang it. Okay. Well, you'll have 5 questions then for sure on Tuesday that'll cover 3.1. All right. All right. So thanks for being here, everybody online. Andrea, good to see you again. You're always welcome. That Zoom code is good for life, and you're an honorary member. So everyone else, be safe. Have a good day. Y'all can go. All right. Be careful around Colin. Bye-bye.